Hello, my name is Travis English. I work with Kaiser Permanente and I run our facilities planning and design engineering team, which basically means I run the owner's engineering design review team. And I want to give you a flavor of what that means. In 2018, Kaiser Permanente completed 145 projects where the project budget was over $500,000 outside of California, over $1 million in California. And the scope involves significant MEP systems. So it's kind of in the ballpark of about 12 projects per month that sort of move through our shop. My team is about 5 engineers, so really that's only like 2.5 projects per engineer per month. And we typically, or ideally, we typically touch those projects about 4 times. The first one is in schematic design, where we see the schematic design basis of design. Maybe that's the early design development. The second time is towards the end of design, where we sort of check or confirm that the final design has everything in place. Then the third thing that we do is we look at the commissioning plan to make sure that the commissioning tasks and what's necessary to validate those systems and get them working is represented in all the construction schedules. And then finally, we look at the final commissioning report to make sure that everything worked, all the issues got resolved, and all the systems work according to their design intent. So if everything went perfectly, we'd have each of our engineers would have about 10 project touch points per month. And this job would be really easy, and we would spend most of our time, reading philosophy books and things like that. That's my goal, but we are far off of that. That's not happening anytime soon. We've got a great deal of job security with what's happening in the portfolio now. I want to show you some of that. So in terms of quality assurance, these are our commissioning numbers from 2018. Kaiser Permanente recently implemented an enterprise-wide system of record for project managers, that's eBuilder. Hopefully you're on it and I'm somewhat familiar with it. And to give you a picture of what quality looks like sort of at that system end, these are our commissioning numbers, right? These are major projects. These are projects that were over $2 million in budget. We had 58 major projects that should have done commissioning in 2018. 20 of them actually produced a final commissioning report. That is less than a 50% success rate right there, which is not good. And then if you actually go and read those commissioning reports to find out what I think are some perfectly reasonable questions, did all the issues get resolved and did all the systems work according to their design intent? Only 2 of those commissioning reports actually got to the point where they stated that those things were true. Now, that's not a very good track record at all in terms of mechanical system quality. And we can blame everyone, right? We can blame commissioning agents, we can blame contractors, we can blame controls contractors or project managers all day long. And believe me, I'm marching down all of those roads individually. But design engineers are not without scrutiny, right? If you go and ask the commissioning guys or the controls guys what the problem is, they tend to say, hey, the problem is that your design engineers just aren't doing what they need to do. So today we're talking about design. We're talking about design quality assurance. My best estimate right now is that there are about 60 MEP design firms working on Kaiser projects. I'm sure that you can understand that's probably too many. It's very difficult to manage quality in a pool that's that wide, right? So if you were Kaiser, realistically, you probably want to get that down to about 1/3 of the number of firms. So if you're a design engineer, that's kind of a double-edged sword. Kaiser needs to find the best engineering outfits that we're working with and keep working with them. But we also need to trim the ranks. We need to get rid of a bunch too out of the program. So let's talk about high quality in design engineering. What is quality in design engineering? I know that sounds like sort of a nasal gazing question, but it's important. And I'm sure that you realize if you're running a design firm, you realize that the answer varies by the audience, right? To your architectural clients, it has to do with service quality. It has to do with meeting deadlines, being able to work on a production team. It's also your ability to help them get work sometimes, interviewing well, developing business well, that sort of thing. Contractors are always going to be interested in the completeness of your drawings, the constructability of your designs, and your ability to work with them as cost issues come up for them. Right? To our Kaiser project managers, it's going to be kind of a combination of those things. It's responsiveness, it's meeting deadlines, it's teamwork, It's details and completeness of drawings. And then there's commissioning agents, which are kind of peers to the designers, I think of. And that they're always going to be very interested in the completeness of the designs and all the details that are involved in completeness of the designs. So that's a lot. That's a lot for a firm to do and do well. And I'm going to be honest with you, having a national quality assurance team like Kaiser does is not going to make that any easier because I won't take anything off this list. My team just adds a couple of sort of higher level points to this list. So here's what quality and excellence in design actually looks like to us, to my team. And I'll admit, it's a little bit selfish based on our position in national functions. First off, the designs have got to be cost effective and value driven. Our central mission at Kaiser Permanente is affordable healthcare. So one of my bosses says that I should use the word affordability every day in a sentence. And so that one counts for today. And yes, we're tracking costs. We know what chiller plants cost. We know what air handler projects cost. We're very, very aware of the costs and our willingness to spend money on and get value out of it. Secondly, your design needs to work, and it needs to work well, because we are passing this over to our clients, our medical group, our operating engineers. Those guys know my name, and they know the name of my team members, and they have our phone numbers, and we carry Kaiser business cards. And so when systems fail or they go haywire, whether they're brand new or 10 years old or 30 years old, we are the line of response. We're responsible. And so the standards that we have, our Kaiser standards, are supposed to provide quality. We're supposed to control for that, right? And then finally, your designs need to be energy smart. On the HVAC side, we have got to provide energy smarts within our designs. Kaiser Permanente has very lofty energy goals, which I didn't get into today, and I'm not going to get into today. But suffice to say, our capital program needs to reduce Kaiser's energy signature, and I'm responsible for that. If we spend $500 million in the next 5 years changing out air handlers and chillers, there is every expectation that that will reduce our energy signature at those medical centers. It absolutely has to. We can't spend money and make our energy worse. We can't spend money and keep our energy the same. We've got to be making things better everywhere we go. So that being said, without further ado, let's talk about the top 5 design issues for mechanical design firms that you'll see from my team when we do your design review. And you'll notice the word calculation is probably the most common word here, and that should strike you as a theme. We're looking for load calculations, we're looking for ventilation calculations, we're looking what I call 8760 calculations. We are looking for acceptance criteria that are stated by the design engineer, and then we are very interested in controls design. So let's talk through those. First off, load calculations. This matters obviously because this is how we're sizing our systems. And so we are absolutely looking for trace output for the systems. We're looking to see a set of assumptions. We're looking for things to fall within certain ranges, obviously. And if they fall outside of those ranges, we're going to want some explanations. And we're very interested in the idea of calibrating these to reality. That's the part that our industry misses a little bit too often. But think about this. Every building system that you have designed for the last 10 years is out there in the field with digital sensors connected to it, and those digital sensors are generating data on the real-time operations of those systems. And so we've got to be able to calibrate these calculations that we're doing in computer models to the reality of what we actually see going on in the buildings. My long-term hope is that things like trace will disappear, and we'll use historical data off of our building systems to predict the future loads, right? So let's go through some examples of where that goes a little haywire. One example is that engineers tend to get equipment lists of medical equipment, and then they read the nameplate electrical data, and they put in some diversity factors, and then use those in the load calculations. Well, we can't do that. That's crazy, because we have plug load studies. We know what the plug load signatures are for hospitals and clinics. We need to be using that data to go after, not a theoretical, diversity factor. So in existing buildings, I urge you to make it common practice to gather trends that show what's going on in that system. My engineers ask for that very often. We want to see trending in the existing system. We want to see the data that supports the design ideas and how that's going to work. I'll go through a couple examples, some funny examples, what I think are funny examples. Maybe you won't think they're funny. But one of my favorite examples was a boiler plant that we were reviewing. The engineer had sized a set of boilers for some buildings and wanted our review. And so we simply pulled the utility bills. We looked at the natural gas bills for the last couple of years, and you can take 1 year's worth of natural gas and simply divide by 8,760 hours, come up with an hourly natural gas use at the site. You can even do that by month if you wanted to come out with an hourly natural gas use in February, for example. And the reason I remember this particular project so well is that one boiler, there were 3 boilers, but one boiler in the proposed plant was exactly 5 times the annual average hourly natural gas load. So the average condition was a 5-to-1 turn down on one boiler, and we had 3 boilers specified. So that's why we're very interested in, let's take these calculations that we're getting out of our systems and calibrate them back to reality as often as possible. Water tanks are another funny example. If you're sizing a water tank for 72 hours of water, do your calculation, but then take a look at some bill data, right? Check it against reality and ask us because we have that bill data, or ask our facilities engineers because they have system data, we have trend data, and we want to share it with you and make those designs smarter. So ventilation calculations. We've got to do ventilation calculations. In hospitals, ventilation is the #1 and the primary energy driver. In medical office buildings, this slide has to do with medical office buildings. So for medical office buildings, this is pretty simple. We do want to see your standard 62 calculations. Those are the same calculations that you submit to USGBC. I know there's a couple different ways to do that. USGBC has a spreadsheet. I believe ASHRAE actually has a spreadsheet that they publish. And my understanding is that the latest versions of Trace can actually do those calculations right in your load calculations, which is pretty cool. For hospitals, those ventilation calculations are significantly more complicated. And we're actually starting to run our own set of ventilation calculations for every hospital project as a means of checking and doing peer review. The entire part 2 of this presentation is going to be about hospital air handler calculations. And the short version is, for Kaiser Hospital work, VAV calculations are a requirement. Variances to OSHPD are a requirement. Those aren't optional. And so there is quite a bit of calculations that need to be done. We'll talk about that in a little bit on this presentation. And then finally, or I guess third up, are what I call the 8760 calculations. These actually matter a whole lot more than your load calculations. I like to say that in a normal design, we design for the sort of peak hour of summer, and then we design for the peak hour of winter, which means that we've designed for 2 hours of the year, and that leaves us 8,758 hours for which we just don't even have a design. And we can't do that. We've got to calculate 8760 hours, right? If you've never seen an 8760 line calculation, they're pretty easy to come by. You can output it out of either Trace or your energy modeling software. It outputs all the variables for the design year, and you can pick which variables you want to output. So you can look at hot water GPM or air handler CFM, supplier temperatures, whatever you want. And we want to look at these. We need to see your load profile. This spreadsheet that you're looking at here is a template that we have. That we'll share that template with you. You're free to use it. But we want to see the narratives that are based on what comes out of these 8760-hour calculations. And it's a pretty radically different way of looking at design. This example here comes from one of our medical office building projects. And the one on the left there is for air handling unit CFM. And you can see it's an air handler designed at about a CFM per square foot, nothing unusual about that. But if you look at the load profile here, you'll see that 80% of the hours of the year, the calculated air is less than 0.3 CFM per square foot. Well, that could be a real problem because the standard rooftop package unit can only turn down to about 30 or 40%. We've seen some rooftop package units that can only turn down to 50%, which would be an outright bust with this design. So most of your year, you could be in a position where you're not optimized and not super energy efficient, or in fact, having trouble keeping your compressor alive. These 8760 line counts are particularly important in chiller and boiler systems because those systems spend most of their time at the minimum position. So you need a very good design for that minimum position. What's the minimum flow at the boiler? What's the turn down capability of the pumps? What's the minimum output of the boiler? How are you going to prevent cycling? Boiler manufacturers talk about things like 10-to-1 turn down on your boilers. But if you look at that example on the right there, that's not a mistake. The difference between the peak heating and the 80% heating requirement is a 600-to-1 turn down. That's what the plant needs to be capable of. That's what the pumping system needs to be capable of. Most of our systems run really, really inefficiently, not because we're selecting inefficient equipment, but because our system design just simply doesn't accommodate the most common operating conditions. And we want our systems to be radically energy efficient at the most common operating conditions. So that leads us to acceptance criteria. What the hell is an acceptance criteria anyway? We have design firms say all the time, hey, that's not even in my scope of services. I was never hired to provide acceptance criteria. That's not in my contract, right? We actually hear that quite a bit. Well, here's the thing. When you're commissioning the system, there's going to be a trending period. It's going to last about 5 days. And the question is, how do we know from the data that we gather in those 5 days that the system is working perfectly, hopefully, according to your design intent? So here's another way to think about it. Think about it this. Let's say that it's 10 a.m. on a Tuesday in April and it's 69 degrees outside. How much CFM should we have at the air handler? How much outside air should we have at the air handler? What temperature should that supply air be? How much water should we see in the heating system? What temperature should the water be? What temperatures do we expect the return water to be, right? Now, if you're anything like me, you may be sitting there thinking, well, crap, I don't know the answers to any of those questions. Let me first tell you that's not unusual. Most design engineering firms that we've talked to about this, including some people that I consider to be some of the smartest on the planet, have a hard time here. Our industry, I believe, is very behind on this. And so you don't need to feel too bad about that. But I do want you to feel bad because this is a big problem. As design engineers, it really has to be our job to define successful system performance. We can hire controls guys to make it come true. We can hire commissioning guys to validate it. But we, the design professionals, have to tell them what they are looking for, or else they can't go out and look for it. So let's talk about acceptance criteria themselves. There are really two types of acceptance criteria. There are in-control criteria, and then there are the energy and functionality criteria. So the first thing to think about is, what do we mean when we say the building is in control? If we just want to say this building is in control, and I'm using quotes around the words in control, what does that actually mean? Well, it shouldn't be that hard to define, right? All the rooms should be plus or minus 3 degrees of their set point. The supply air set points for the air system should be pretty well known. Those are typically a function of outdoor air temperatures, maybe something else. And the supply air temperature set point should, the actual supply air should be plus or minus 2 degrees of that set point. That's in control. And again, the heating hot water set point or the chilled water plant set point should be pretty well known. It's generally a function of outside air temperature or maybe outside air temperature plus a couple of other variables. And whatever set point we are striving for, we should be there. We should be plus or minus 2 degrees of whatever that set point is. So if you could just say those things, hey, all my zones are plus or minus 3, all my temperatures, those main system temperatures are plus or minus 2, you have achieved control. You have a building that's in control, right? Now, it may be a complete energy hog or a complete dog, but it will be in control. And that's when it's safe to move occupants in, by the way, is once the systems are in control. Then you have to look at energy functionality. So we need a set of acceptance criteria around energy functionality. And again, those should come out of the design intent. If there's an economizer on the unit, we should be able to look at a few variables and predict the position of that economizer damper. And then we should be able to go measure the damper and boom, it matches, right? Based on the capacity of the cooling system, we'll have an expectation of a certain input power, or kW per ton. So that gives us an expected kilowatt, and we should go out there and measure the kilowatt on the chiller and it match. Or it shouldn't be double, right? It should be plus or minus 10 or 20% of what our expectation is. The same with the heating system. And we should actually know what the CFM is on the air handler, or at least we should know what the anticipated fan power should be in any given hour of the year, and we should be able to look at it, and it should be within reason, or it should not be out of whack, right? Now, I know what some of you are thinking, some of you at least, you're thinking, well, the trending period is in an empty building. Our systems won't really work until the building is occupied. That comes up time and time and time again, and yes, you are right, you will not have normal occupant loads during the trending period on most projects, and you do need to take that into consideration. But let me tell you this, and I'm speaking from hard-won experience here. If the energy systems on the project are not working before the occupants show up, adding occupants to the building has never once fixed those problems. And we've tried it, and we've tried it more than once. But if the energy systems aren't working before people walk in, they ain't going to start working when people walk in, right? The important part of this whole acceptance criteria thing is that we need to define system performance in a set of acceptance criteria. And these have got to be in the project documentations. We want to see them in project specifications, typically the control spec. We have one design engineer who's putting these directly onto the plans so that they're right in the construction documents. We also need to see these in the commissioning plans. They need to be hard contract requirements. And we really need to identify the points that need to be trended in order to validate the system. The whole point here is that they have to be objective, not subjective, because commissioning happens during the 9th inning with 2 outs. Everybody wants to go home, and that is the wrong time to start arguing about whether or not the supplier temperature is acceptable or not. We need to define that way in advance, and then hold to it at the end of the job. Okay, so the last of our top 5, number 1 or number 5, whatever you want to call it, is controls design. Controls design and the sequence of operation. So I would ask you, if you're watching this, ask yourself, how many hours have you spent logged in to a building automation system and working inside a building automation system software? Do you think you've spent 100 hours logged into a building automation system? That would be 2 weeks full time, right? Do you think you've spent 1,000 hours logged into a building automation system, which is kind of like 6 months full time? It's important to keep that in mind. Our field engineers, who we're going to turn this over to, are going to spend between 500 and 1,000 hours per year logged into the building automation system. And at a hospital site, there might be 9 of those engineers. The control system and the interface of the control system is absolutely the face of your design. If the controls are shit, then your design is shit. And there's a hard truth here. I'm going to be perfectly honest with you at the risk of offending you. Design engineers are not the engineer of the control system. There is a programmer who works for a controls company, a controls integrator, and they are going to write the code for those controllers. And that individual spends 2,000 hours a year working in control systems. So if they're 5 years in, they've got 10,000 hours logged inside of these systems, which means they are at least 2 orders of magnitude more experienced in those systems than any design engineer I've ever met. That's the real engineer of the control system. And when it comes to programming controllers, he's smarter than any of us in the design side. But we all have to agree that this is insanely critical. It is beyond critical. And we're not the experts. So what are we going to do, right? So what we need to do is, during design, we need to write down as much as we can. If there's not a controls guy on board, then we really need to assess the system as much as we can. When my team sees a single paragraph or a single line that just says, expand the existing control system, that's a red flag for us. For existing systems, we want to see an assessment of the existing system. What is the hardware? What's the version of the hardware? What's the software? What are the graphics? We want to see a plan that's written out for how the new design is going to happen. how it fits into the existing control system, how it lands onto the network, what pieces of hardware are getting added or what points are getting added to the existing pieces of hardware. Big tip is to take pictures. Take pictures of the controllers, take screenshots of the existing control system. And I am not at all kidding. Pull out your phone, shoot a photo of the air handler screen, crop it, and drop it in your basis of design. That at least tells us that you've been in the same room as that computer, and it shows us what points are mapped onto that air handler screen, which is insanely important. For new systems, we're going to need to see the design intent. We want to see that written down, and we're going to want to see that written down really as early as possible in design. We need to see what those control things are and what the optimizations are that we're expecting, and a set of acceptance criteria. What is considered to be successful system performance? Now let's talk practically though, because as I said, most of us in design engineering field are not actually the engineer of the control system, and we are, compared to the guys who program control systems, vastly inexperienced in this. So in order to procure controls, we're going to need a set of controls details, control specifications, and written sequences, right? So the best thing to do, the smart thing to do, is to outsource and supervise that design using a set of parameters, right? Use off-the-shelf sequences wherever possible and cite their sources. So we tell you to use ASHRAE Guideline 36. Title 24 actually has some intended sequences of operation. So does ASHRAE 90.1. It's better to just write the intended sequence there in plain language and not try to do details. Don't invent things. Don't use non-custom standard sequences that you've written in your design firm. Don't write detailed custom sequences that force controls integrators to create unique or new pieces of code. We don't want unique or new pieces of code. We want code that works, and hopefully code that's already been used before. I don't think that any of our jobs are inventing systems. I hope that our jobs aren't inventing systems. So get the integrator's preferred sequences, right? Why not have your integrator give you the air handler sequence that meets your design intent, and then use that if you've already got an integrator selected, right? And if you use a sequence on the drawings, let everybody know under what conditions you will accept substitutes to that. What are the acceptance criteria that you're looking for as markers of success? And then finally, get it reviewed. Get it reviewed by the commissioning agent. Get it reviewed by an integrator. Get it reviewed by the facilities operators. Get it reviewed again, and then get it reviewed again. We always have commissioning agents on Kaiser projects, or at least we always should. They need to review the hell out of the sequences. The integrators need to review the hell out of the sequences. Again, if the controls are crap, your design is crap. But as design engineers, I like to emphasize as much as I can, you're responsible for the design intent. The details of that design can be outsourced or can be supervised by you. Okay, so part 2 of this presentation is going to be about air handling systems, how to design an air handler in a Kaiser hospital. But before we do that, I'm just going to hit some potpourri topics that always come up when we talk to design engineers. First off, pharmacy clean rooms. We have a specialty review program for those. So if you're doing a pharmacy clean room, then you need to get in line for the specialty review. We do those certain days of the month. We have a guideline, follow the guideline. We have standard controls, use the standard controls. We will give you the plans from previous designs. Don't reinvent things. Use as much as you can, steal as much as you can from the previous jobs. Operating rooms, again, we have some standard vendors. We have memorandums of understanding with 2 vendors that provide operating room systems, and those operating room ceiling systems test out at ISO 6 and a certain microbial count. And so we have performance guarantees on the cleanliness of the room from those vendors. So use those vendors, use the standard design. Don't try to get smart and tell them how much CFM to use. Ask the vendors how much CFM do you need in order to meet your performance assurance, and then let the vendor design basically the system. We do have standards that we want open control systems. So we are looking for multi-vendor control systems, multi-trade control systems. That tends to be Tritium Niagara. And so we do have a preference towards that. We require integration of our controls. And so if you're doing a project that involves lighting controls and HVAC controls, make the decision early on. First up, it's required by our standards that you make the decision to integrate those controls. Don't find yourself at the end of a project saying, well, I didn't think that we were going to put the lighting on the same system, because it absolutely is an expectation. PEX is okay. We're fine with PEX piping. We're using PEX piping in a lot of our potable water systems, even heating hot water systems. So we're fine with PEX piping, no problem. PVC piping is not okay. Kaiser Permanente has a ban on PVC piping from an environmental perspective, so we can't use that. The med prep rooms have become a problem for us in our design. Those refrigerators are 24/7, and so any type of, they tend to ruin any type of energy optimization sequence that you can imagine. And so we always check those on our project to make sure that they're dealt with in a way that lets the rest of the systems function. The shelved pharmaceuticals is also a kind of a unique issue for Kaiser. We tend to have medical office buildings where we have outpatient pharmacies that don't stay open 24/7 like a retail pharmacy would. The medical office building will be open 9 to 5 during the week and then closed on the weekend. We do need to maintain those shelved pharmaceutical spaces between 50 degrees and 80 degrees 24/7. And so we need to have a design in place to do that. Okay, air handling projects. How to design an air handling system for Kaiser Permanente. Or what we're moving towards, what we call the Air Handler Center of Excellence. First off, get your scope right. We are reviewing air handler projects extremely closely, and we're not going to accept sort of anything less than what you're going to see presented here in the next half a dozen slides. So make sure that you have a scope in place with your project manager that represents everything here. There's going to be a pretty intense pre-design investigation report, design calculations. If I didn't make it clear before, we have high expectations around your design calculations. We do need a written basis of design that's going to have acceptance criteria in it. We expect every Kaiser project where you're doing an air handler in one of our hospitals in California to submit a variance to OSHPD and get that variance accepted. That is part of your responsibility. And then you produce your drawings and your specifications. So our scope is pretty heavy, and make sure that you have that covered. So pre-investigation and pre-investigation report. People have asked us if we have a BOD template that we want you to follow, and right now we don't, but I'm completely open to that idea. If you guys have one that you use, I'd be more than willing to adopt it or develop it into a standard BOD template. Right now, we really have more of a checklist approach, and you can see what that checklist is. 9 times out of 10 on air handler projects, you're working in an existing building. So the investigation report you need to write needs to demonstrate a profound understanding of those existing conditions. And I like that word. When I was in business school, we read this guy, Michael Porter, this guru on business strategy, and he said, a good business strategy is one that demonstrates a profound understanding of the competitive environment. Right? A profound understanding is one that's characterized by great knowledge or intense insight. It's a level of understanding that normal humans do not ever attain. And that's what we need to get to in this pre-design investigation report. Pretty literally, we want you to completely investigate the air handling system. There should be no question that gets asked at the end of scoping that you cannot answer and answer very confidently, right? It's a high bar, make no mistake, it's a high bar. Then of course, design calculations. We get it, right? We expect calculations for air handling projects. If you have some feedback from the facility, it is probably fair to assume that the peak load calculations done by the previous engineer aren't undersized. That's probably fair, right? So generally the CFM that you find in the room is okay for peak loads. But what we're really going to need here are the 8760 hour calculations. So we do need to have an understanding of the profile of those loads, even if we're just sort of doing that in a spreadsheet and putting the peak loads in place. Our standards provide some of the assumptions. We have the hospital plug load studies. You can use that as a resource. I believe the 2 that we have actually show a load profile as well as an average load, so you can use those. The lighting loads should match the lighting design. There's some good data out there from NREL and UW on hospital lighting energy profiles. We do have some standard supply air temperatures. If there's already digital controls in the space, Again, you can calibrate your load calculations to the trend data, to the actual data, and that helps key your load calculations to reality. If you have some supplier temperature trends and some valve position trends, for example, that helps to get a gut check on the numbers that you're coming up with. For humidifiers, we really want to avoid them as much as possible. In California, OSHPD allows us not to install humidifiers if we don't have the design conditions to need them, or if we can show by calculations that they are not needed. Our rule of thumb is that if humidification is needed less than 400 hours per year, then installing a humidifier does more harm than good. So if you put in humidifiers, we're always going to ask the question to see those annual calculations and the psychometrics around them. I'm going to talk about ventilation calculations on the next slide. And we talked quite a bit in the previous section about the 8760 load calculations. One thing I want to point out here that's kind of specific in hospitals is that we do have rogue zones to deal with in design. A rogue zone is one zone that screws up your strategy. And on a patient room floor, the classic example is the med prep room, which has a refrigerator in it, so that generates heat load 24/7. So you may want to reset your air systems to 67 degrees, in neutral conditions, but the med prep room needs 55-degree air. So your whole system winds up at 55-degree air. Your energy signature is horrible all year long. We have to be able to identify that stuff in our load calculations, right? I was talking to a design guy the other week, and he said, "Really? Are you joking? Do you really want me to calculate the supplier temperature for every room and every hour of the year?" And the answer is, I don't actually think that that's what you need to do. I think there's smarter ways to go about that. Which brings us to ventilation calculations. Ventilation calculations for a hospital system design are not easy, and they really shouldn't be. This is advanced ventilation system design, and so that's what we're doing here. If you're using a spreadsheet one time and showing it to OSHPD, then you're probably not doing nearly enough work. We've developed this spreadsheet tool that you see on the screen here just to peer review the calculations that our design engineers are doing. You're welcome to it. Obviously, we'll share it with you. I think most firms have their own, or they have something like it, and that's fine too. You can use that. But there are a couple steps that I see as being important, at least, in my opinion, and with people that I've talked to. The first step is that you're going to have to do a system maximum air calculation. That should be at the block peak, not the sum of space peaks, or at least I'm told. So this one is for a 7,000 CFM air handler. The sum of the zones might be 8,000 CFM, but you should be doing your ventilation calculation, your outdoor air calculation at the maximum simultaneous peak. The second calculation that you need to do is at the minimum occupied position. And I call this the spring 3 a.m. condition. So you basically assume that it's 3 o'clock in the morning and the temperature outside equals 72 degrees exactly the temperature inside. So there's no external cooling load, there's no external heating load. Occupancy is at a bare bones minimum because it's 3 in the morning, so you're probably 500 square foot per person or less. And you basically need to identify the minimum CFM and at the same time identify the supply air temperature that you're going to be able to set back to. In my mind, the ideal supply air temperature for that condition is 67 or 68 degrees, where you only have 2 or 3 degrees delta T in the space. But you need to look back at your load calculations. This is where those rogue zones will show their face, and this is where that med prep room can become a problem. And then finally, the third set of calcs you need to do is really for the rooms, and that is to know your unoccupied condition or the unoccupied opportunity. Again, if you're doing new controls, it is our standard to interlock lighting occupancy sensors to HVAC so that you can turn down those rooms. OSHPD lets us turn down the rooms to 20%. If you're following standard 170, I guess you can turn them all the way down to 0. But you need to understand what that unoccupied turn down condition is on a room by room basis. And of course, the entire time you're doing this, you need to maintain balance for all the positive pressure rooms in the system and all the negative pressure rooms in the system. So not going to lie, this calculation is an absolute pain in the ass. It would be awesome if the programmers over at Trace could take this on and get it to a point where it works. But up until then, I think the design engineers are all just using spreadsheets. This is back to calculations, so I don't need to talk about that any further. So let's talk about VAV in the state of California. If you're outside of California, you can skip this slide. But for those of us in California, I'm sure most of us know, California requires a return air VAV box for every supply air VAV box. And in economic terms, that has effectively acted as a ban or a barrier to VAV in California hospitals. It kind of doubles the cost of your air distribution system, which frankly is not a good investment. I know some places have done it. We've done it, but it's really just not a good use of money, particularly when you look outside of California and you notice that nobody else requires them. Right? We have hospitals in Oregon and Hawaii and Washington, and they don't have to do return air VAV boxes. So we have submitted variances to not do them, and we've been successful with that. We have 7 precedent alternative method of compliance, AMCs, that have been approved by OSHPD. The basic idea of the write-up is that if you have an area type smoke detection system, then sort of less than perfect balances between supply and return air in the rooms don't matter much to smoke spread because the fan shuts down quite quickly. So that's how we've gotten it approved. However, when it comes to OSHPD, there is no such thing as precedent. So every design team and every project needs to develop the AMC, submit the AMC, and get it approved. And make no mistake, your OSHPD plan checker may want to reject it. I mentioned that we have 7 approved precedents here, but what I didn't say is that after approving 5 of these, OSHPD did reject number 6, and we had to appeal it. And then they rejected number 7, and we had to appeal it. So you do need to be prepared for that. Absolutely. Our future development is to essentially reestablish standards. When I started at Kaiser, we went through this whole phase of tearing down a lot of standards, which was a good thing. Many of our standards were kind of obsolete, hadn't been updated, and were hurting us more than they were helping us. But we are moving towards effectively reestablishing standards. We need to adopt those standards from successful projects. So if we have a project where the sequence works, that's where we're going to want to steal that for the purposes of national standards. So my hope is, as time goes on, we can make the design jobs easier by feeding you standard components, standard points list, standard names, a lot of standardization around controls, standard optimization sequences, those types of things. And that should actually make the job a little bit easier as time goes on. So that is all I have, and thanks for your attention.